I don't know if any of y'all actually ever go back and watch these lectures, but last class my microphone, I don't know if I forgot to plug in the port up there or what, but the mic wasn't hooked. You can hear me, but it's like far away. And just FYI, if you're ever going to go back and look at that last lecture, you're not going to be able to hear me very well. So just so you know. All right, I have something for you. Get out of here. Mini exam 4. I believe this is the 4th one. I labeled it number 4, so there's a small little edit on this here. These problems actually come from 11.8 through 12.5, not 12.1. So there's a couple of problems here that you can do using Lagrange. And then after that, it's out of chapter 12. So it's due for, 2 weeks from today, I believe. Is that what I've got there? Is that right? March, April 8th? Okay, so 2 weeks from today, that's due. If you are going to do it. But we're kind of running out of time. If you haven't done these, then you're kind of going to start being committed now at this point to do these. All right, we are going to pick up where we left off. All right, so we were talking about double integrals. And we had talked about when we're doing double integrals, the most important thing to us is the region in which we are integrating over. And we started out by integrating over a rectangle, and then we did a type 1 region, and then we did type 2 region. Do we need to recap that, or are you ready to get right in? Get it right in? Okay. So here we have our first problem that is not just like directly telling you what the region is that you're integrating over. This is more kind of like a word problem. We're going to have to extract, look at this and extract the double integral from the information somehow. So we want to find the volume of the tetrahedron that is bounded by these 4 equations. Here's the next mini exam. Okay, due 2 weeks from today. All right, so first of all, tetrahedron, we did this back when we were learning about vectors. We talked about tetrahedrons. Tetrahedrons are something that looks like, I don't know, that would be an example of a tetrahedron, all right? And we're trying to find the volume of a tetrahedron where it's bounded by this. What is this if I draw this in 3-dimensional space? That's a plane. And this is also, well, it's a line in 2-dimensional space, but in 3-dimensional space, it's also a plane. And this is also a plane. X equals 0 is the YZ plane, and Z equals 0 is the XY plane. So this is like the ground, right? This is like one of the walls here in the room. Actually, Z equals 0 is the ground. X is 0 is this wall. That's the YZ plane. And then we have some other plane that does not have Z in it. So Z is a free variable. So that means that we have a plane that's like vertical, but it's got some sort of tilt to it, right? And then we have this one, which is truly like a plane that's tilted in 3-dimensional space. So we're trying to find the volume of it. So how can we do this with a double integral? Well, let's first try and draw this the best we can. I'm going to try and draw it in 3-dimensional space first. let me go with x being here, y being here, and z being here. Let's try and figure out where this plane hits the x-axis, the y-axis, and the z-axis. Right? So where would this hit the x-axis? So if you're on the x-axis, what can you tell me about y? If you're on the x-axis, what can you tell me about y? Y is 0, and z is 0 also, right? If you're on the x-axis, your y and your z are 0. So if I replace y and z with 0, x must be 2. So that means if I go out on my x-axis 2 spots, I have 1 point. That point is on that plane. If I can get 2 other points, then I have a plane, don't I? So let's figure out where it hits the y-axis. So you let x be 0 and z be 0, and you get 2y equals 2, so y is 1. So if x and z are 0, we get y is 1 here. That was 2, so here's my y. And then, where does it hit the z-axis? At 2 also, right? So you let x and y be 0, you get z is 2. So we go up 2. There's 2. We have another point. And so you can imagine, I hope, that there is a plane that goes through those 3 points. Now that plane extends in every direction, doesn't it? Like it keeps going out in every direction, but that's a good way of representing it with that little triangle. Now, we want to know the volume of the tetrahedron that's bounded by that plane, so bounded by this plane, z equals 0, which is the ground, right? Z equals 0 is the bottom here, so that's that piece right there. That right there is z is 0. Of course, this piece right here that's kind of tilted, that's the equation. Well, let me put it this way. Z equals 2 minus x minus 2y. What I've done there is I've solved this plane equation for z, and because I've solved it for z, you can actually look at z as being a function of 2 variables. Does that make sense? So that plane, you can look at it as a surface, a function of 2 variables. All right, x equals 0. Where's x equals 0? That's this back side, right? This right here, that piece. That piece right there is x is 0. Are y'all kind of seeing this coming together here? We have z is 0, which is the bottom. We've got this back wall. We've got this plane that's here. And now we have x equals 2y. So let's draw x equals 2y in 2-dimensional space. X, y. X equals 2y is the same as y equals 1/2 x, right? We solved it for y. And that's a line. So we can graph this line. Has a y-intercept, x-intercept of 0, so it goes through the origin. Has a slope of 1/2, so up 1 over 2. So it goes up 1 on the y, and goes over 2 right there, and it would be this line, wouldn't it? Now let me try and draw that line over there. So let's just use the same points. So I'm kind of like kind of looking down like that. It goes through here, right? That's the origin, that's this point. And then I want to go on the x-axis. I'm going to go on the x-axis 2 over, right? And 1 on the y-axis. So x-axis 2 over, 1, 2, and then up on the y would be here. Do y'all see that? Y'all see my line on the ground there? Now it extends backwards also. That's the line, but in 3-dimensional space it is a plane. So since z is free, we can imagine that this thing just kind of goes up. Do y'all see that? So I hope you can see the region we're talking about. The region we're looking at, see, I'm out of colors here. Let me try my best to fill this in. It's going to be this back side right here. Bless you, bless you, bless you. Okay, that's enough, please. And then you have this back side, which is on the z-axis, right? And then you have this right here, which is on the y-axis. That makes up one wall. And then we have the bottom, which is here. And then there. That's the bottom of the thing, right? And damn it, the way I have it tilted, it's hard to see this, but it's going to go from this point down to that point. Do y'all see that? Yeah. That's where this plane, this blue plane, like slices through. Yay or nay? Yeah. Yeah? Okay. So that thing right there, we want the volume of it. So what we can imagine doing, I like kind of looking at it like if I took a light, okay, a light from the top on the z-axis and shined it down, the shadow on the ground would be that triangle down here, wouldn't it? That is my region of integration. That's what I'm integrating over. That's my region, my domain on the bottom. And those points within this triangle on the ground are getting mapped up into that surface, aren't they? Yep. And that would create that top little angled edge, right, or angled surface. So I want to know the volume below that surface down to the ground, right? Down to the ground? Yes. So let me try and draw another picture. Try and do a little bit better picture. I'm going to exaggerate a little bit. I have this, 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 let's see, this. That's that same piece. I'm just kind of tilted it a little bit. This part right here is my domain. Okay, that part on the ground, which is where over here? What is it over here?
The area under the curve from 0 to 2.
So from here to here, is it this piece right here, or is it the top part? It's the top part. It's kind of hard to see this. But this continues this way, right? Like this. And it goes over like that and over. So you've got to kind of tilt your head. What am I missing, I guess? I'm missing something in here.
The slant part?
Yeah, this part right here, right? This part right here. So we're not talking about this piece right there. That would be this. That would be that, wouldn't it? Yeah. But we have another line that comes through like this. Right? So our region of integration is that right there. This right here. That's our D. You follow me? Sure? This gets pretty visual, I guess. Okay. Let's see. So our D is that bottom part. Now, if we're going to do a double integral, what I need is a top surface and a bottom surface to be able to find the volume. I need a top surface and a bottom. So what can I use for my top surface? This thing right here, right? This is my top surface. Solve for z. That's my top. So this piece right here is that. But what's the bottom piece? What's the bottom of this? I know it's my domain, but as a surface, what can I call that bottom? Z0, right? That's Z0. That's the XY plane. So maybe I'll go back in my notes and I'll remind you. That's pretty much what we're looking at there. Let me bring that up. We have a domain on the bottom, right? Some domain on the bottom. We have a bottom surface, which we'll call G of xy, which is this one. And we have a top surface, which is the f of xy here. Right? So we have a top and a bottom. The volume of this is going to be the double integral over D of the top surface minus the bottom surface with respect to area. So that's what we're going to use. But we still need to get our heads around what this domain is. So let's talk about this domain. I think I'm going to blow it up, make it a little bit bigger. We have 2 here, 1 here. This is 1. And we have a line coming across like this, and then another one that goes like this. And we are interested in that piece right there. So what type region is this? Is this a type 1 region or a type 2 region?
Type 2.
So how do you tell the difference?
If it's like y equals or x equals.
Uh-huh.
And so since that one's like to the side, it opens to the left, it would be x equals.
So you could actually look at this either way. This is both a type 1 and a type 2. Remember how I did it last time? I said if you were to draw like a little rectangle in here, is your top curve and bottom curve changing, or is it the same the whole time? So here, if I draw my rectangle there, or I draw it here, or I draw it here, it doesn't matter where I draw my rectangle. Do you agree that the top curve, in this case it's a line, the top curve and the bottom curve they're the same the whole time, right? So this would be perfect for type 1. Now it is type 2, but what's the problem if you look at it as type 2? It would change, right? Like if you draw this rectangle, the right curve and the left curve are this curve, this line and this line, that would work until you get to where? That little point. And then it's going to switch, right? Now it's going to be this line instead. So if you're going to do this with type 2, you have to do 2 double integrals. If you do it as a type 1, you can do it as 1 double integral. Yes?
Did you cover again the concept of the rectangle? It's like whichever one's on, like to the...
Type 1, you look at vertical rectangles.
Yeah.
Okay, and you're looking for the top and bottom curves to never change. That's type 1. Type 2 is horizontal rectangles, and you're looking for the left and right functions to not change.
Mm-hmm. Okay,
So,
I see what you're saying.
You sure?
Yeah. 'Cause
Okay.
then, at the top, it's like that first slanting line.
Yeah, like in here, that would be a type 2, and it would be the left and right don't change. But once you get to the bottom part of this, now the right function changes. So you could do it, but it would just be a little harder. All right, let's see here. I drew this picture. If I'm going to do a type 1, so D is going to be a type 1, which means my x's have to be between two constants, and my y's have to be between two functions of x. So what is my x bounded between if I'm looking at this region D? 0 to 1. Now we're assuming that's where they hit. Is that where they hit? I mean, my picture looks like it. How would you verify it? Which equations would we have to solve? Like, what's the equation of this line right here? This was half x, right? That was half x. That's where we got this one from, right? But what about this one? Where did this one come from? It came from this part of the tetrahedron, right? This plane. It was when z was 0, right? When z is 0, that's when this plane came through and hit the ground and created that line. So what we would be doing, let me erase this one. To find that point right there, we would be having to set z to 0 here. Okay, so you get x plus 2y equals 2. And you're trying to solve that while simultaneously solving this one. Right? You're basically trying to figure out where these two hit each other. Which is at 1. Right? I'm sorry, not 1. It's actually where? When x is 1, yeah, it should work out. If x is 1, you should get, yeah, it should work out. 1, 1/2. The y coordinate doesn't matter. The x coordinate's the only one that we really need to worry about. Solve that for y, set them equal to one another, you get x. Right? Solve this for y, set them equal to one another, you get x is 1. So am I okay to just jump to this and just trust that you could solve those two equations? Sure? Okay, so our x's are bound between 0 and 1. What about the y's? What's the lower bound of my y's? It's this function, right? Solve for y. So this is 1/2 x. The important thing is that y is not between two constants. Your y is not between two constants. It's between two functions of x. Your x is between two constants. Your y varies between the two lines. So that's my lower bound. What about my upper bound? What's this line right here? Well, we never did it, but it's this one solved for y. So it's that, right? So this is negative 1/2 x plus 1. Are y'all following this? I know there's a lot of geometry happening here, a lot of visualization. Are there any questions where I'm getting any of this? Yes?
Can you explain one more time, like why, so I understand that the x were between two constants, but then how come you know that the y would be between two constants?
Because this region is not a rectangle. If this was a rectangle, then your x goes between 0 and 1, and your y goes between 0 and 1 also. But what's really happening here is that we're just letting x move along. So we're saying, okay, let's let x be right here. Now, if x is right there at exactly the value x, then my y coordinates are between there and there, aren't they?
Oh.
So my y's would then have to be between 1/2 of that value and negative 1/2 x plus 1 of that value. So it's bounded between those two curves. So it's like you fix an x, that dictates what y is. Got it?
Yeah.
Okay. All right, so we have our bounds on x and y. Now we set up the double integral. So our double integral should be, remember we're doing double integral over the domain D of f of xy minus g of xy dA. Top surface minus bottom surface, right? Top surface minus bottom surface. Now my D here can be switched over, and I can put limits of integration. Which goes first? The constants go first. 0 to 1 first. Then we do our 1/2 x and negative 1/2 x plus 1 there. And that's going to now force our order of integration here, isn't it? dy dx. So dx is the outside one, because this are restrictions on x, and dy is here because this is our restrictions on y. And remember, I also said you could put like y equals here. Y equals if you want, it's up to you. And then inside, we put the top function, or the top surface, which for us is what?
2 minus x minus 1.
Yeah, it's this thing solved for z, which is 2 minus x minus 2y. And then subtract from that the bottom surface, but the bottom surface was z equals 0, so we're really subtracting nothing from it. And that's it. That's our setup.
And just to be clear, like just to state the obvious, each time we solve with C, and then we what makes our two equations.
For our top and bottom, yes, but you might have to determine which is the one on top and which is the one on bottom. That you might have to. Here, this was the take home. Due 2 weeks from now. I think the three of you, on that, it says on there that it just covers stuff from 12.1 to 12.5, but there's actually stuff from 11.8 on that test also. All right, we good? And then now what you would do is you would integrate this with respect to y first, right? Do y'all want to take this one all the way, or I don't care. We can do just this one all the way if you want. Okay, we'll go all the way with this one. All right, so the first integration I'm going to do is integrating everything with respect to y. So here's my inner integral. I'm going to do the antiderivative of this with respect to y. So I should get 2y minus xy minus y squared. I'm going to evaluate that from y equals 1/2 x to y equals negative 1/2 x plus 1. And then after I'm done with all that, I'm going to have to integrate that again with respect to x. We're all comfortable with this? Okay, now I'm going to replace what with what?
The y's with
Y's with this, and then subtract from that y's with that. So integral 0 to 1, and then I have two big nasty things that have to be subtracted here, then dx. So let's go replace them. Okay, so 2 times y is first, so 2 times that, right? I'm going to just write negative x plus 2. That's what happens when I multiply this by 2. And then I'm going to do this again, but this time times x, right? X times that, or negative x, I should say, which should change this to positive half x. Shouldn't be x squared? X squared, and then minus x. I'm doing this kind of mentally here. So multiplying this by negative x, you get positive 1/2 x squared, and then minus x. And then we have to do minus that thing squared, right? That sucks. Okay, so minus that thing squared. All right, so I'll have to figure out what that is. Then take away from that, let's plug in 1/2 x for y. So when I do that here, what do I get? Just x. When I do that here, minus half x squared. And then when I do that here, this one I think I can square in my head. So I'll have minus, when I square this, I get 1/4 x squared. Integral 0 to 1, I guess I'm not ready yet. I'm going to clean this up. It's going to be, let's see, minus x is minus 2x. I guess I can do it all at the end. Minus x plus 2 plus 1/2 x squared minus x. All right, let's square this. So if I square that, I get 1/4 x squared minus x, I believe, because you get half and half, and minus half, and then you get plus 1. So that squared should be this, right? And then I'm supposed to subtract it. So minus 1/4 x squared plus x minus 1. And that takes care of all of that. And then I have to come through and subtract this, so minus x plus 1/2 x squared, and then plus 1/4 x squared. So that's my, I don't need parentheses and brackets, that's kind of overkill, but we good with that?
The 1/4, oh, it's a 1/2.
This one right here?
Yeah.
I
1/2 x squared.
Let's see, negative 1/2 x plus 1, negative 1/2 x plus 1. I'm starting to not trust my arithmetic as age gets a hold of me here.
Oh, okay.
Right, and then this is minus 1/2 x, then another minus 1/2 x, and then plus 1. So these together gives you negative x. Nothing like, we get some canceling, right? Like that one and that one.
The 1/4 x squared also cancels.
With, oh yeah, that one cancels, good, good. And so how many x's do I have? Let's start with the x's.
Oh, wait.
Shouldn't the 1/2s cancel as well?
This one and this one? No, because one's positive, they're both positive, right? But they'll go together and just be x squared. We'll start with the x squareds,
Yeah,
okay.
'cause on the first one you squared negative 1/2 x, and so then,
Where, here?
yeah, and then you added the, wait.
I think we're good. This and this are going to go together to give me that, so I've done that. How many x's do I have? Minus x, minus 2x? So that takes care of that and that. And then constants, just plus 1. Actually not too bad at the end of the day here. And that's just your basic integral from Cal 2. We'll double check it on the computer here. This is 1/3 x cubed minus x squared plus x, evaluating 0 to 1. So when we plug in 1, we get something. When we plug in 0, it all goes away. So we're just going to get 1/3 minus 1 plus 1. Ooh, 1/3? 1/3? I feel the need to check. Oh, here, no, we don't want that. Let me go back to this. Just do a new one. So this is one cool thing with this program, Mathematica. You can do integrals within integrals. Make that a little bigger so you can see it. So we wanted to go from 0 to 1. We wanted to go from 1/2 x squared, or yeah, 1/2, sorry, what was it? 1/2 x, right? It was 1/2 x to negative 1/2 x plus 1. And we are integrating, help me out, 2
Minus x minus 2y.
2y, and we're integrating that with respect to y, then x. Okay, 1/3. A little easier on the computer. That's why I said, remember on the test, the final, right? You're gonna want to, I'm gonna want you to just set these up, get me the double integral set up, and then move on to the next problem. Because really, once you get it to there, I mean, we can really turn to computers to help us out. But see, a computer's not going to be able to take that information and create the double integral, right? That's the part that you need to be able to do. On the take-home exam, I do want you to do the integrals by hand all the way through, but I would use, go ahead and get on Wolfram Alpha and see if you can check your answers. That'd be a smart thing to do. All right, so we're done with that one. All right, so this is an example of a problem where the order might matter. Sorry, I've got like a splinter or something. All right, so we want to do this double integral, and they just give you the double integral. All right, they just give it to you. Let's ask my computer to do that. It was 0 to 1. 0 to 1, and then it was x to 1. Whoa. X to 1, and then here's where things get real weird. We have sine of y squared. Sine of 1/2 squared. That seems like it should be sine of 1/4 then, right?
Or is it sine of 1/2 squared?
No, then it would have had this in brackets and then the squared on the outside. All right, so that's what the computer got. Let's see here. Let's just think about this right now. Does anybody feel like integrating with respect to y first?
No.
Do you know the antiderivative of sine of y squared? No, you are not going to have any luck with that. In fact, let's ask my computer just to integrate, not a definite integral, but just to try and find the antiderivative of sine of y squared with respect to y, because that's what we would have to do at some point, right? Okay, let's see what, whoa, Frenzel function. It brings up a Frenzel function. What the heck is that? Well, see, we have no idea what this is, right? No idea what this is. And so that, if it's going to spit this out, there's no way we're getting this. No way. This is kind of like in Cal 2, there should have been certain integrals that you were shown that you just can't do with any techniques. Now, we could do a power series for this, but that's not what we want. We want to do it in a more efficient way, if possible. Have I at least convinced you that integrating with respect to y is not something we want to entertain at this point? Yes? Okay, so what we're going to do is we're going to take a look at our region D. Let's talk about the region of integration. Can you tell me, just by looking at this integral, what x is between and what y is between? So what's x between here? 0 to 1, okay. And y is between x and 1. So let's see if we can't visualize that. X goes between 0 and 1. right? But our y is between two functions. One of them is, the lower one is x. That's y equals x, right? So that's this line. That's y equals x. And then the upper restriction on y is the constant 1, which would be that line right there, 1. Agree?
Yes.
Okay, so this is our region of integration right there. And we're treating it like a type 1. In this integral, we're treating it like a type 1, right? Could we write it as a type 2?
Yes.
Yes, we could. If we write it like a type 2, then our rectangle is going to go this way, right? And so if we try it with a type 2, and why would I be wanting to go type 2? Just, maybe I've missed this part. I'm not stressing why I would look at it as a type 2. What would doing it as a type 2 allow me to do to this double integral?
Flip it.
Flip the order of integration, right? Which means I'd integrate this with respect to x first, which I don't mind doing because this would be then a constant, wouldn't it? And then I wouldn't have to integrate sine of y squared. Does that make sense? With respect to y. So maybe by changing the order of integration, I'm going to be able to get the integral. We still have to see. But if this is type 2, then your y's are between two constants, and your x's are between two functions of y. So what constants are my y trapped between here? 0 to 1. Okay, so that's not that different. But now I'm looking at this rectangle this way. So the left is like the lower one, and the right one is like the upper one was. So what's my lower bound, no matter where I go with my rectangle here? 0. And then my x upper bound is this, right? But solved for what? Solved for x instead of y. So, I mean, but this would be the upper bound, or the right-hand side bound. X is y. So this is my function of y that is my upper or right-hand bound. So this would be y. Okay? So now my double integral, I can rewrite it from 0 to 1. And then I'll put it here like 0 to y. And then now this becomes dx dy on the outside, switching the order of integration. And I'm integrating sine of y squared. Now when I integrate that, I'm going to integrate it with respect to x first, right? So let's see how nice this becomes. So this will become integral from 0 to 1. Here comes my inner integral. The antiderivative of sine of y squared with respect to x is what? X sine of y squared. Or you could put the x in the back, but I'm going to put it in the front. So that's just a constant times x. And I'm going to integrate that from what to what here? Be real careful. X equals 0 to x equals y. So that's why sometimes I say it's might be worth it for you to put like x equals here and x equals here. The reason I know it's x is because I'm integrating with respect to x first, and that's why I'm going to be replacing my x's with these. And then after I'm done with that, I will integrate with respect to y. So let's go in here and replace first x with y, and that will be nice. And then when we replace x with 0, it kills it off. So my new integral becomes, y goes there, so it's y sine y squared dy, right? That's it. Right? Because y went in here, we got that, then 0 went in there, and we got nothing. And look at this. Isn't this going to be easier to integrate? This is just a basic u sub, because this y saved us, didn't it? Because now the derivative of y squared is 2y, and we have it out there, but we're off by a constant. So I'm just going to do a little bit of u sub over here. I'll just finish this problem out. What I'm going to do is I'm going to look at the indefinite integral first. So I'm just going to come over here as scratch work. I'm going to just figure out what this antiderivative is. Basic u sub, u is y squared, du is 2y dy, and that means I'll replace that with u, right? And then y dy, I have that right there. So I just have to scale this by a half. I hate this part of this class because anytime I actually do like a u substitution or integration by parts or trig sub, like people are taught different ways on how to do this. So I'm just going to trust you could do this. If you do it a different way and get the same answer, great. All right, that's what as long as you can get to it. This new integral becomes 1/2 sine u du. So antiderivative of sine is negative cosine. Plus a constant of integration, but this is going to wind up being a definite integral anyway. So this is just going to turn into negative 1/2 cosine of u, but u was y squared. So the antiderivative of y sine of y squared is negative 1/2 cosine y squared. So I think I'm ready to get to the answer here. We have this equals the negative 1/2 cosine y squared evaluated from where to where here? Go 0 to 1, 1 to 0, however you want to say that. And then this is equal to, let's plug in 1. So we get negative 1/2 cosine of 1. And then minus what? When we plug in 0, what's cosine of 0? 1, right? So cosine of 0 is 1, so we get minus negative 1/2. I think we're getting negative 1/2 cosine of 1 plus a half. That's what we got. That's not what the computer got, is it? What did the computer get? It was like sine of, I think, 1/4, right? Sine of 1/4. There's got to be some trig identity that would get us to sine of 1/4 here. I'm trying to think of what it might be at this point. Yeah, I can think I see it, but we don't need to verify it. We could just do it. We could just do it algebraically. Like, I think the computer said the answer was that, right? So we could like figure out what that is. Yeah, there's an identity. The identity I'm seeing is this, like pull out a negative 1/2 out of this, and you get cosine of 1 minus 1 like that, right? And then there's some identities like what is cosine of theta? How is that related to like sine of theta? They're off by, right? They're like shifts, so that we might be able to do it that way. I really don't care as long as the answers are right. As long as the answer is right, I don't care about the identity. Let's just check it here. Let's go back to this one, the first one up here. I'm going to get that as an answer. So the answer to this should be, can y'all see it over there? 0.229849, something like that. That's what the computer says. So I'm going to just grab my calculator real quick and see if I get that answer here. And I have to make sure that I'm in radian mode here on my calculator, which I am. So I'm just do this one right here. So I'm going to do cosine 1 minus 1, and then I'm going to divide that by negative 2.0. Yeah, it's the same thing. Okay, so we got the same answer. So the moral of the story here is that if you have a double integral where your inner integration is something that you're not going to be able to handle, you might consider drawing the region. And y'all understand that from this you can draw the region, right? Just this right here allows you to go draw the region. And then you can say, okay, look at that region. Can I look at it as a type, the opposite type? Whatever this is, the opposite of that. If you can, then you can change the order of integration and things can get better. Not always, but they can. So the order might matter in which you do the integration. I know for a fact there's a problem like that on the final, where you're asked to change. It actually, the directions are something like change the order of integration. So they want you to take it, change the order of integration, and then integrate. I say they. By they, I mean me. All right, here's something that we should know now about double integrals. And I kind of discussed this a little bit. If your region, D, happens to be the union of two other regions. So if I take D1 and D2, if I put those together in one big pot, I get D, right? So if you break up your region, capital D, into two smaller regions, then you can basically take your double integral over D and break it into the sum of two double integrals over D1 and D2 respectively. Does it make sense that it would work that way? Okay, that's just a property, and you don't have to guess as to whether or not that's true. There's a proof for it that if D is the union of two regions, then the double integral is just the sum of the two double integrals over D1 and D2 respectively. Okay, this one is a big one. This one is a huge one right here. So here's what I want to do before we do this. Okay, I'm going to draw you something, and I want you to tell me what the volume of it is. Draw you a box. Okay, I'm going to tell you that this is 2, this is 3, and that is 1. What is the volume of this? 6, right? So let's say this was in feet. Feet. The volume of that would be 6 cubic feet. Agree?
Yeah.
Now, what is the area? The area of the base of that. So what is the area of this? It's 6, but it's 6 square feet, right? So it's 6 square feet. Y'all okay with that? All right, now I want you to look at something else. What if I tell you you've got this cylinder? What if I tell you the radius of this? Boy, that doesn't look like a radius. What if I tell you the radius of that is 5 inches? And I tell you that this distance from here to here is 1 inch. Then what's the volume of this?
25 pi.
So it's the area of the circle, right? The area of the circle times the height. So this would be 25, that's the area, pi r squared, times the height. What's the height? 1. So this would be cubic inches, right? What's the area of the base of this? What's that area? What is it? 25 pi square inches, right? These numbers are the same only because what?
The height is 1.
The heights are 1. Do you agree? If I change that to 2, then these won't match. If I change that to 10, these won't match. But if I leave this, if the height of the object I'm looking at is 1, then the numerical quantities are always going to be the same. So arbitrarily speaking, if I have some arbitrary two-dimensional, imagine on the ground, some two-dimensional shape like this, then if I tell you that the height of it, that's going to be hard for me to reproduce that. Oh my gosh, I already messed up. You get the idea, okay? Who cares? But if I tell you that the height of that is 1, then aren't the volume and areas the same? Yes? Okay, you sure? So what I'd like for you to now consider is that in all of these problems, we call the bottom here D. D. D, that's our domain on the ground, right? And then this top piece right here, this top piece is our top surface. And since I want it to be 1 unit high, I'm going to just define it to be 1. And wouldn't that be a surface that's exactly 1 unit high? Right? And then what would the bottom surface be here? G of x, y. Well, that's the ground, isn't it? So that would be 0, right? Y'all with me?
Yeah.
So the double integral over D here of the top surface, which is 1, minus the bottom surface, would be 1. With respect to area, which is double integrals over regions D are always with respect to area, this quantity actually gives you what? This is the volume. This represents the volume under here down to there, right? But that is numerically equivalent to what? The area of D. The area of capital D. All right? This is a special property of double integrals, and that's what I'm about to put up on the board. As long as the height is 1, then the volume and the area are numerically equivalent. 6, 6, 25 pi, 25 pi. And that's what the next note is saying. The next note says, the double integral is the area of D. If f of xy is 1, if we define the height of the surface to be 1, then the double integral over D of that surface will be the double integral over 1. That is representative of the area of the D. Okay? We're going to use that to prove some pretty cool stuff here in just a minute. So let's see if I have an example to go with this. Don't think I do, but let me see. No, I don't have an example, but we will do one in the next section. All right, this is number 24 from the book, so I'm going to have to break my book out real quick. And you know what? I have 20. Yeah, we'll do 24. This is from 12.2. So that area formula I just gave you, just put it on the back burner, all right? We'll use it in a little while. Okay, for this one, find the volume of this solid. Okay, find the volume of this solid. It is the solid that is enclosed by z equals x squared plus 3y squared, x equals 0, y equals 1, y equals x, and z equals 0. We have a solid. The solid that we're trying to find the volume of is the solid that is enclosed by those things, whatever they are, okay? Find the volume. So let's start with the easier parts. X equals 0, right, is the YZ plane. So that's one of the walls. Z equals 0 is the XY plane, so that's the ground. Y equals 1 is a plane, isn't it? So back in our picture here, y equals 1 means go out this way 1, right? And hold that constant, so it's a plane that goes like this, right? Back that way. That's y equals 1. Y equals x. What does that look like? So this was x, this was y. Y equals x is the diagonal. It's a plane that does this, right? And then that. And what does that look like?
A cylinder opening towards the Z.
Not quite a cylinder. It's not like a beer can. It's more like it's like a bowl, okay? It's like a bowl. So it's a paraboloid, all right? So if you go back to your quadratic surfaces, that will help you figure out what that looks like. So I have something like this. Let's just take a first shot at this. Here's x, here's y, here's z, So let's start with the bowl. The bowl is going to open up like this. I don't know, something like that. Okay? That bowl just continues up forever. X equals 0. So z equals 0 is the ground, right? It's the ground. Y equals x is a plane that cuts through this way. Boy, it's going to start to look like a disaster. Can you tell this is going to start looking like a disaster when I start to draw this? Y equals 1 is a plane that cuts through this way. I mean, how do you draw this, right? I mean, this is difficult to draw. You'll agree with that. So what I think works the best here is to try and visualize the domain on the ground and then come back to this. So let's try and see what the domain on the ground looks like. So let's try and put all these together. And I'm going to start x equals 0. So x equals 0 is this. Right? That's x is 0. Remember, this is x and this is y. Y equals 1. Would look like that in two-dimensional space. Y equals x would look like this in two-dimensional space. And z equals 0. Z equals 0 is where?
The whole XY plane.
Yeah, it's actually this whole plane, right? And then this part is the bowl that's above it. So can y'all like visualize the bowl coming out of the page like this? Yes? You have a bowl, that bowl right there. We're kind of looking straight down like that. We have this bowl that comes up like that. We're trying to find the volume that's bounded by this bowl, the ground, z equals 0, and then this plane, and that plane. Remember, these come out at us. So do you see D? Do you see capital D? It's this triangle right here, right? That's your triangle. Right there. That's your D. Does that look like a type 1 or a type 2? It could be both. Let's go with type 1. Okay, let's just go with type 1. If it's type 1, we're going to need to figure out where these hit each other, right? So where do those hit each other? When this is equal to this, right? So set these y's equal to one another when x is 1. So I know that this is 1, right? We know that this is 1. So as a type 1 region, we have our x's are stuck between two constants and our y's are stuck between two functions of x. So x is between 0 and 1, right? And what's y between? X and 1, right? X and 1. Because the bottom one is x, the top is 1. So not between 0 and x, right? Between x and 1. Questions on that? Now we need to figure out what's the top surface minus the bottom surface. That's the part that goes in the integral, right? So what's the top surface? The bowl, right? The bowl is the top surface. What's the bottom surface? Z equals 0. So I don't think I can draw it any better than I just did, but we have f of xy, which is going to be the top, right? The top surface is going to be that solved for z, which luckily for us, it already is. And then the bottom is going to be g of xy, which for us is just z equals 0. So that's everything we need to set up the double integral. 0 to 1 here, x to 1 here, top minus bottom, d what, d what? dy dx. There it is. That double integral represents the volume between all of these surfaces. All right?